So we have just imported geometry into the ICM CFD. You can look at the surfaces, points, so this time I would go for the tetra mesh, and the next time I will go for the blocking. So here I need to set the sizes. Before that I need to set the parts. So right click and create part, and I will call this one as the in y, that is on the top side. Uncheck other two options and just select the face, and then we have the in z. And here we have the this outlet. I need to change the name of this in y because we have the extra hyphen sign here, so just click on done and you can save the project. And the last part we are going to make is the outer wall. Then I'm going to make the separate part for the points. This time I will only choose the points here, then the curves, uncheck the curve option and check all other options to only click on the select the curves. Again save the project. Also define the material point as a fluid. It should be selected in such a way that this point should lie inside this pipe. You can delete this solid 1 save the project. For the meshing purpose, as we know, the diameter is 0.15. So if you want to make the circumference of this one is going to be the 0.15 into the 3.14 pi d. So if I want to resolve this circle into the 30 points, it means I divide this circumference by 30. My size should be the 0.0157. Okay, and but based on this size, which is a 0.1, so into 3.14, and maybe I need to divide this one into 30, so it's a 0.0104, so the 0.01. So I will go for this inlet y 0.01. Again for the inlet z also 0.01, for the outlet 0.01, point wall maybe a 0.01, apply. And in the global size I can go for here 0.04, click on apply. This size is going to be there. You can also check the size on the different parts. I think I should change the size of the wall to the maybe a 0.04, and then need to apply the size function of the 0.02. Elements and gap is 10, refinement is 40, apply. Now just go to the compute mesh and click on the compute. Okay, I'm going to change the size of the wall to the 0.02, and the global size is, this is okay, just okay. Maybe here I can make it 0.01. Again compute and replace the old mesh. Okay, just delete the volume mesh, go to edit mesh and just delete the volume mesh and smooth the surface mesh with the quality required up to the 0.8. Now you need to run the alternative loops of the Laplace smoothing and without Laplace smoothing, and you should run this one up to the when we don't see any change in the mesh quality further. So this time it's 0.5534, 0.5538. okay, keep it doing 0.5528. okay, now we stop the smoothing process, and the last step should be the without Laplace smoothing, and then we just go to the mesh, and here I'm going to create the volume mesh based on the Denali method. Click on compute. You can check the cut plane from the inside of the mesh. You can also display the volume. This is the internal volume. You can also have the view in the along the middle Y plane, and you can just move it downward to see the mesh inside this longer pipe. Okay, all right. Next step, I'm going to create this prism mesh. For this I need to select the part, so this is going to be the wall. Click on compute. So you can see this prism mesh here, also over here. Okay, now we need to make the some more layers from these layers of the prism. So I will just divide them into the three layers each. Apply. So now total we will have the 9 layers, and then I need to smooth them. So I will use this tool, and I will keep the size as a 1.2. This seems fine. Now you can check the quality again. The quality is now around 0.2, and if you want to smooth it, you can just freeze the penta and smooth the other elements. So it's a 0.337 in the previous step, now it's a 0.344, so it is improving. Okay, now I will make it float, and maybe quality requirement is very low. Okay, undo. Okay, again check the cut plane. Okay, you can again delete the volume mesh and create the Denali mesh. No, I think we should delete now the whole mesh. Okay, change directly to the robot to the this quick method. You can try the smoothing steps I already displayed. But this time I'm just going to make the mesh to be ready for the analysis. Okay, again the same 3 layers and a smoothing step. Now go to the output mesh and here select the solver, which is a Fluent, and the boundary conditions for the surfaces for the inlet via its velocity inlet. Copy this one and apply the same condition on the inlet Z. For the outlet, I will choose the pressure outlet, and for the wall, I will choose the wall condition. Save the project and output the mesh data. Okay, now I will go to the Fluent. Choose the path, CFD courses, this multi-phase course, workshop 1, 3D, double precision. Okay. Open the mesh file. Check the mesh quality. It's a 0.26 good quality, and the aspect ratio is 40, and the maximum orthogonal skew is 0.65. There's no error of the minimum volume as well, so just save this as a Tjuction. Okay, now in the models I will choose a K epsilon resible and with the scalable wall function option. In the materials, we are going to use click on the create edit. We are going to use the Fluent database, and from here choose the water liquid, copy and close it. Also, you need to use this new material by the Fluent for your current case. So the material here you should change to the water liquid you just described right now, and you can also delete this material if you want it. And in the boundary conditions for the inlet y, we are going to put the value as 0.3. You can keep the option that is a magnitude normal to the boundary, or you can choose a magnitude direction. In this case, you're going to put direction of the flow, which is going to be the in the minus y axis. So here you need to put the value as a -1. Or the better option is to use normal to the boundary, because we don't have any angle, so we don't need to put the in direction over here. So this is the best method to put the option normal to the boundary. So you can change these things also. So going to be the point it's going to be the 0.1. Okay, put the value also here as 0.1. Okay, so for this inlet y, it was different in the previous case. I think here we had the y and here we had the z, but here now we have the y and here we have the z. So no problem, we put the condition like as per this geometry. For the inlet z is going to be the 0.3 meter per second, and here diameter is 0.15. Click on OK, and the next thing is the or pressure outlet boundary condition. So there is okay, something else we should be putting here is that for the this case for the inlet z, and also you need to change this energy equation. You should enable this energy equation because we are interested in the heat transfer problem. So now in the thermal field, I would be putting the value in the degrees Celsius. So I will change the units to the Celsius, and here in this case the bigger pipe, I'm just going to put the value of temperature as a 15 degrees Celsius, and the smaller pipe over here I'm just going to put which is coming from the basically y, I'm just going to put the value as a 25 degree Celsius. And in the outlet, although it's not necessary to put these values, but in the case of the backflow, this condition will be used. So again, this is a bigger pipe, so I'm going to use the diameter of the 0.15, the diameter of this pipe, and this for this pipe diameter is 0.1. And in the thermal condition I will use sum of average conditions of the both inlets, which is 25 and the 15. So its average is going to be the 20 degrees Celsius. This is only used when they are the backflow. Okay. The solution scheme I will use coupled, and maybe you can use pseudo transient if needed. Okay, so we will try this one. And the solution control, keep the default values, and then you need to change the monitors, put more zeros here. Also you need to maybe create some surface monitors, so plot it and make it area weighted average pressure at the inlet Y. So we'll just see the progress of how solution is converging, and initialize solution with the hybrid option. Okay, now run the case, put the number of iterations to the 300.